Hi guys, Holloway here. Today we're talking about angular momentum, its causes when it's conserved, and how it relates to linear momentum. So we're going to make a lot of references back to linear momentum because the two are analogous to one another. So keep in mind that we know that linear momentum is a vector, little p equals mv, and the direction of momentum is the same as direction of velocity. We said that linear momentum was the strength of motion. And so really we're looking at, it's the same strength of motion idea, but this time it's the rotational strength of motion. So angular momentum is how hard would something that's rotating be to stop it rotating is kind of the idea. So the normal way you'll see angular momentum is a capital L. So capital L is angular momentum, and then it has two forms that can be written in. I omega, I call that the standard form, although there's one and the other are interchangeable, but this is the one you'll see the most. L is a vector, it has direction, and its direction is the same as omega, which we're going to give by clockwise or counterclockwise. So for rotation, we're going to talk about which way it's spinning, and that will help us keep track of things. Angular momentum, the units are kilogram meter squared per second. So it's kind of a lot to remember. There's no nickname for it yet. But you can remember by multiplying the moment of inertia, which we know is kilogram meter squared, times radian per second. But you will notice that that little term radian will disappear from the final answer because radians times anything drops out of the equation. So watch out for that. But this is our unit for angular momentum. Okay, the other way of writing it is L is equal to mv r perpendicular. So this is still going to have a clockwise or counterclockwise direction to it. But what we're going to look at is, so what's happening is an object is moving linearly, but they want to know what angular momentum it has. And your brain's going to keep telling you, well, if it's going a straight line, it's not rotating, therefore it has none. But that's not necessarily true. So what we're looking at is what's going to happen in the future. So if you see down here under angular momentum, it says angular momentum of an object moving straight about a future point, a future pivot point. So I'm going to come back up here and draw you a little scenario here. So imagine we have a flat frictionless surface and there's a little block. It's moving this way. It has a velocity of 2 meters per second. Oops. 2 meters per second. And it's going to strike and stick to some rod that's hanging down. That has a pivot point here. It's on some sort of a wall scenario. So we've got some sort of a block here that is attached to it, connected to the ceiling, so that this can rotate this way when this block smacks it. They're going to stick together, we'll say in this case, so the block and the rod will rotate up. So what's going to happen in this situation is the angular momentum of the block. So the L initial, which is of the block, is going to equal L final over here of the block and the rod rotating together. So we're going to look at what is the angular momentum about the future pivot of the block. So that's what we're going to measure. So when we do mv, that's pretty easy. So we'll have the mass of the block here. We have a velocity. It's this r perpendicular piece. This is the challenging piece to get. So it's r perpendicular to v. So what we can do is we can take the v vector and kind of sketch it out into space. Just go forever that way and that way. So we extend it, and then we say from the pivot down, that would be r perpendicular. Now, because our block has no actual, we don't know how tall it is this way, we will just put this R all the way at the end of the rod here, is basically what they'll have you do on the AP exam. So if they said the length of the rod was L, they won't worry about the fact that the pivot's not at the very end and the block's not at the very end. They'll just have you use the L of the rod because it is perpendicular to the velocity vector in this position. But that's what you have to look for. You have to find the R perpendicular in each case. Okay, and that's a little challenging to find because it's about a future pivot point. It's not rotating yet, but it will be later. So that is different than the linear momentum. Linear momentum is just mv, and when it strikes the rod, the two should drift to the right, but they don't because it's anchored to the ceiling. And so it will only rotate, and that's what makes it challenging. Try to remember, linear momentum never turns into angular momentum. So it's the angular momentum around a future pivot that we're actually looking for. I shouldn't write it here because that's going to confuse you later when you look back at your notes. But they don't turn into one another. So each type stays separate. And so we want to find them individually. Okay, so angular momentum before collision is equal to angular momentum after, just like linear momentum before collision is equal to linear momentum after. And that's true whenever, remember for linear momentum, if there were no outside forces, then there was nothing to change the system. So the system had to have the same momentum before and after. So for rotating objects, we're going to say if there's no outside torques, if the net torque from the outside is 0, then angular momentum will be conserved. Okay? So all objects within a system must be accounted for Li to equal Lf. So when we had blocks hitting before linearly, and then they ended up sticking together and moving like that. So we had to count for 1, 2, 3 pieces in the system, the before pieces, the initial, and the final. So same thing with angular momentum. You have to account for all the angular momentums of the system before the interaction or collision and all them after. So we are going to look at conservation of angular momentum, and this is a scenario where both objects are rotating. So if we have a situation, and I had a picture, well, we'll get to the example in a second here. So you take the angular momentum of the first and the angular momentum of the second. That'll be the total before the collision. And the angular momentum of the first one after and the angular momentum of the second one after. And so it looks just like the m1v1 plus m2v2 equals m1v3 plus m2v4. It really is the same equation, just written with written with the angular variables. There is one extra thing we have to watch out for, and that's that the moment of inertia is not changing. So if the objects are rigid objects, then the I should remain the same, unless they move the pivot point. Do you remember the ice skater and how she moves her arms and that changes her I? So if you have a non-rigid object, it doesn't have to, I may change because of the collision. And that becomes really, really hard. I don't expect this, but if it does, then you have to look at I before for each one and I final for each one and put those in place. So watch out. You may have to look for those. That's a really challenging problem to do, but it is fair game for you guys. So rigid objects is what they normally use, and the I doesn't change during the collision. A non-rigid, like an ice skater, because her arms can flop around or something like that, can change. Okay, here's an example of two rigid objects. The one on top is spinning about this axis here. This first disc here, disc 1, is a mass of 1.2 kilograms, a radius of 0.5 meters, and has an omega naught of 6 radians per second. It's going to be allowed to fall along the axis, and then it's going to rub down here. So you're going to have some friction that's going to create a torque on the bottom one, and that will create a counter torque on the top one, right? Third law, every force equal and opposite force, so every torque equal and opposite torque. And so you're going to have the top one slow down and the bottom one speed up until they reach the same speed. And then eventually it's going to kind of look like, this is a hard picture for me to draw, kind of like a birthday cake, where they're on top of each other and the axle's like this. So now they're spinning with one omega. This would be omega final. And they both have the same omega at the end. So we set it up pretty simply. We're going to do angular momentum of the first object before the collision plus angular momentum of the second object, which happens to be 0, equals angular momentum of the system after. And now the nice thing here is the two have the same omega final, so we can just add their i's and multiply it by omega 3. So the first one is 1/2 m1 r1 squared is I of the disk, times its omega, which was given as 6. I didn't put any numbers in. And then here we have I of the first disk plus I of the second disk, whatever that total is. We can take that total and divide it over, and that would leave us with omega final. And so that way we know what the system, that would be how fast the whole system is rotating in the end. Example 2. So I've got some extra drawings on here. I'm going to clean this up real quick here because I don't like that. So I'll explain it as we go through here. Okay. Let's look at this. Sorry about that. So we have a box that collides and sticks to a rod so that both rotate after the collision. So this is going to be a case of the momentum before, so L before is going to be mvr perpendicular. So whenever you see something moving with a linear velocity, you're going to have to use that. Now, again, it doesn't have angular momentum yet, or so it looks like, but it's the angular momentum about the future pivot. So that future pivot is what it has angular momentum about right now. Even though it's not wrapping around it yet, that's how we apply the idea. And so when we do Li, the rod is sitting still, so we only have the angular momentum of the block. So R perpendicular in this case, if we extend V out in space, then hopefully you can see that the length of the rod is perpendicular to that. And so R perpendicular, in this case, we're just going to call L, which is this 2 meters. So before I have the mass of the block, its velocity, and then R perpendicular, which is the length of the rod in this case. Now we're going to let the box stick to the rod, so together they'll form one moment of inertia. And so if you think about it, we have this long rod here and some box of unknown size, unknown dimension. You guessed it, a point mass. So we have a point mass being added. That's a little PM up here. So that's just going to be mr squared of the box plus a rod that's rotating about its end because the pivot's up here at the end. So that's the 1/3 ml squared. So be careful you don't put both masses in for the rod. This is only the mass of the rod, and this is only the mass of the box. So they're each multiplied by different factors because the length of the rod, well, in this case, the R away is the length of the rod. So I take that back. They're both 2 in this case. So if you combine them, it wouldn't have messed up, but you got to watch out for that. Sometimes they're not the same. But we can take this total for the new I of the system and divide it over, and that would give us omega final. So from here, they like to then say, so if this is now rotating up that way, how high will it rotate? What theta will it get to before gravity slows it down? Because gravity's putting a counter torque trying to slow it down. So when we find omega final, that's right at this moment when it's still vertical before it starts moving. Right? It has that velocity, it's going to swing up and slow down. So as it goes higher and higher and higher, it's going slower and slower omega. So we go then to the conservation of energy idea. And the kinetic energy it has at the bottom, 1/2 I omega squared, will equal the potential energy it has when it stops at the top, which is mgh. Now here you have to be careful. We would not want to use h of the bottom. That's not going to go because the bottom is going to go to a different amount of height than, say, like this point or this point. We want to use the center of mass. So this is the center of mass. If this was L over 2, the middle of the rod, the center of mass because of this block is going to be a little bit lower than the middle of the rod. But you'd have to solve for that using the center of mass equation. So you do that R1 M1 plus R2 M2 over M1 plus M2. And that's going to give you a location of where the center of mass is. So you'd want to label that on your picture. Then we would say that from that center of mass to where it is later, that is going to be our H. That's how high the system goes. So the height of the center mass is how high the system goes. And that's the H that is up here in MGH. So then we know from one of our first equations that H is equal to L minus L cos theta. But again, here we're talking about the height of the center of mass. So we have to use L to the center of mass. So this distance from the pivot that we found to the center of mass. is what goes in for that L to find our unknown theta. So that was a big add-on to angular momentum, but that's where they can take it next, going to conservation of energy and going from a rotational energy to a potential energy due to gravity. All right, I think that's enough for today. We'll work on problem solving this week. Bye, guys.